also welcome all our online viewers who have joined us on the live YouTube webcast. As you all know, we celebrate this day, October 30th, every year in fond memory of Dr. Homi Bhabha's birthday. May I request the director, Professor Sandeep Trivedi, to begin today's program by garlanding Dr. Bhabha's photograph. Thank you, sir. I now request Professor R. Vijayaraghavan, convener of this year's Founders' Day Committee, to say a few words.
Good afternoon, everyone. A very warm welcome to all of you present here and also our online viewers. First time we are webcasting our program live, and hopefully there are members of our various centers who have been able to join us today. So very warm welcome. Special welcome to the director, Professor Trivedi, Chair ACCC, Professor Vatagaonkar, Wing Commander Anthony, Registrar, and our special guest, Professor Chengalur from NCRA. This is a really special Founders Day, and I think not many of us know that today is actually the 50th Founders Day to be celebrated. During the Silver Jubilee in 1970s, in the 1970, they decided to celebrate the birthday of Dr. Homi Bhabha as the Founders Day. So this would actually make it the 50th Founders Day. And as many of you know, we are also celebrating 75 years of founding of TIFR. And as if that was not enough, this is also the 50th year celebration of graduate school with 2 days of events planned for the next 2 days starting tomorrow. So this is indeed a very special Founders Day, and it has been an honor to serve as the convener of the Founders Day Committee. And we have put in a lot of work in the last couple of months to get this program. As we all know, we celebrate Founders Day to both remember and honor the contribution of Dr. Homi Bhabha to the TIFR family. The style of celebrations sort of mark the unique, multifaceted personality of Dr. Bhabha. As we all know, he was not only a world-renowned scientist, but he was also a great administrator, an institution builder, and also an artist. His love of arts is actually on display. There's a new archive exhibition, and I would like you to invite you to check it out. And today's function, we will actually give recognition to the academic achievements of our students, excellence in teaching of our faculty, and the hard work and long-term commitment of our staff and faculty, to name a few. In addition, on November 3rd, Sunday, we will have a day-long event with sports activities and science mela in the morning, and a popular sounds lecture, ultimately culminating in a cultural show where the TIFR family will display their various talents on stage. As I mentioned, we also have this archive exhibition and a photo exhibition and Rangoli exhibition, which is now open and will be on display till November 3rd. So on behalf of the Founders Day Committee 2019, I'd once again like to welcome you all to participate in all the activities we have organized for you, and hope you enjoy the events. Thank you.
Thank you, Professor R. Vijayaraghavan. I now invite Registrar, Wing Commander George Anthony, to address the audience, please.
Good afternoon, everybody. Director Professor Trivedi, Chair at CCC Professor Sanjay Vatagaonkar, Founders Day Convener Professor Vijayaraghavan, Professor Chengalur from NCRA, senior retired colleagues who are here, and dear friends, and also all those who are watching us on live. At the outset, once again, welcome to the 50th Founders Day on the occasion of 110th birthday of our founder, Dr. Homi Jahangir Baba. Great institutions and great personalities are not born every day. These great events happened very rarely. To be associated with such an institute and such personality is a great opportunity. So I think we should all consider ourselves very lucky to be part of this great institution, which was founded by Dr. Homi Baba. While we celebrate the Founders' Day today, as mentioned before, we also step into the 75th year of TIFR existence and the 50th year of formation of the graduate studies, for which the celebrations commence tomorrow. While we have three important timelines coming together, unfortunately, we also had a sad event of passing away of our third director, Professor Srikantan, on 27th October at the age of 94. We pray for his soul and also convey our heartfelt condolences to his near and dear ones. Coming back to the Founders' Day, it would be most appropriate to refresh our minds with the accomplishments achieved by our founder, Homi Baba, in such a short period of time. Though Homi Baba spent only about 2 decades of his scientific life in India, his vision went much beyond his own visual range. We have now expanded both geographically and in number of disciplines, and we continue to expand. I think it was his perseverance to succeed and his vision to look beyond that created TIFR and many other great institutions like DAE, BARC, ECIL, etc., to name a few. While in earlier times we enjoyed a lot of freedom in terms of what we did, how we did, and also large amount of resources at our disposal. Now it's becoming more and more difficult having to observe government rules more strictly and ensuring transparency in all our dealing in every little bit. This is making life difficult for us to carry out even our routine tasks due to long-drawn procedures. While this may sound difficult, I'm sure we'll be able to overcome this problem soon with time. This new requirement should not let us waver from the visions of our founder, and we should continue the good work initiated by him. On this occasion, let's take a pledge that each one of us will ensure the best in everything that we do. While our scientists bring out the best in research, let's support them with the best service. We are fortunate that due to foresight of our founder, we have such a wonderful workplace, which is an envy to many in the whole of this country. The least we can do to give back is to put in our best and support this institution to retain its glory, which was envisaged by Dr. Homi Baba. On this occasion, I would like to, in advance, congratulate all students who graduated from TIFR last year along with the award winners. I would also like to congratulate all those who completed 25 glorious years in this institute, and also the winners of the Lifetime Achievement and Sport Achievement Awards. I would also like to thank all the retired TIFR members, especially those who have taken the trouble to come here today, and also those who will come on Sunday, who helped shape our institute to what it is today. With this, I would like to conclude by once again wishing you all a very happy Founders' Day. Thank you.
Thank you, sir. I now request the director, Professor Trivedi, to say a few words about today's event.
Professor Vadegaonkar, Professor Vijay Raghavan, Professor Chenglur, Wing Commander Anthony, distinguished colleagues in the audience, students and dear friends, also especially those of our friends and colleagues joining us on YouTube, including our friends from the other centers of TIFR. A very warm welcome to you this afternoon. As you all know, this is a very special occasion for us. Every year, we celebrate the birthday of our founder, Dr. Homi Baba, and this year too, we gather on this auspicious and important occasion. He was a remarkable person by all counts, as our registrar also mentioned, a scientist of very high repute, an amazing administrator. It's only after I became director of this institute did I realize just how hard it is to combine both attributes. And for someone to combine them at such a high level of excellence is truly remarkable. A great administrator. I think one of the great sons of India, I would like to say. If you look at his contributions in science, in the starting of the atomic energy program, in the starting of electronics, even the thinking about the space program, it's remarkable what the country owes him today. If we are secure in terms of nuclear capabilities, it is due to Dr. Bhabha. It's a great contribution. So a great son of India, a great patriot, I think. Great lover of art, and a very fine human being with the sensibilities of an artist at the highest levels. We were really fortunate to have such a remarkable person as our founder. We are blessed for it. We thank him for this every Founders Day, as we do this year as well. But looking into the future, it's worth thinking and asking ourselves, what would Dr. Bhabha have asked of us if he were here today? What would he have asked of us? Of course, I ask myself this question in my office many days in the year, he was a great scientist. He understood the importance of atomic energy as the entire understanding of nuclear science emerged. And of course, the whole world woke up to it with the atom bomb. But he realized the peaceful uses also of that. Today, there are comparable, I would say to you, great transformational changes in science that are taking place around us. There are great changes in biology. There are great changes in our ability to exploit the quantum world, to do things, Professor Vijayaraghavan is here, to do things we could not have imagined we could do before. Great changes in chemistry, all kinds of things. Amazing developments in computer science and artificial intelligence, which promise to change the world. I think Dr. Bhabha would have been tremendously excited, both by the opportunities and the possibilities that we can harness these changes for the betterment of India, for the betterment of Indians. I think that would have also excited him. And we must reflect on that. We must reflect on that as we go forward. A remarkable opportunity has been given to us by the government. I think, again, it really is because of what Dr. Bhabha showed, in terms of what our institution is capable of doing. Great opportunity last financial year, in February of this year, we were sanctioned 896 crores for Hyderabad, where we can try to do some of these great things. But also, of course, here, also across all our campuses in the centers. And that we must think about. How can we do things in the future that would make Dr. Bhabha truly proud? I think that is really a fitting tribute to him, so that as we go forward, we constantly reinvent ourselves, so that we carry the country's flag in the arena of science, which Dr. Bhabha wanted us to do, while also playing our role in terms of institution building and in terms of being at the forefront of bringing these advances in science to the country for its developmental goals. So let's think about that as we go forwards this year too, and keep alive the spirit of Dr. Bhabha as we keep alive his memory. We have to remember his great love for art and his thinking that we could bring art and science together. The location of this institute is so remarkable. I've had many scientists who have come, really experts in their fields in the world, gone all over the world, and they come to this campus and say, just in terms of aesthetic beauty, it's almost without parallel. You have this great art around you, you have this wonderful location, and I think we need to keep alive that sense of aesthetics in our work as we do in terms of the institutions we create. I'll just end on one small personal note. Dr. Bhabha's research towards the end was on studying slightly technical, but on studying symmetries in the study of particle physics, in the study of the underlying laws. And the way he was exploring this was to ask what kinds of symmetries are manifest in the fundamental particles we see around nature. We have particles like electrons or the proton, and these particles are fermions and they carry spin half. And then we have the photon, which is a boson, and it carries spin 1. And so you could ask, what other spins can occur in nature in terms of the elementary particles, in terms of which the fundamental laws of nature are written or created? And he struggled hard with this. And he didn't succeed in including higher spins beyond spin 1. This is what he was working on. Well, it's a very interesting fact that in my own research in the area of string theory, what researchers have found in our own work connected with this about 2 years ago, is that you can have the higher spin representations appear, but if one higher spin representation appears, all must appear. In other words, once you go from spin 1 upwards to spin 2 and then try to go further, you need an infinite set of these higher spins altogether in a very beautiful formulation. So when I was doing that work, I also spent my time upstairs in the director's office, and I would be struck often by what Dr. Bhabha would think if he were to learn about how his ideas of aesthetics were finding a role in our understanding of the emerging laws of nature. I think it would have made him very, very happy as well. So anyway, a small aside, and I do hope we keep alive his sense of beauty in our hearts as we go forward as well. Thank you. You have to be the master of ceremonies. I forgot to say something which I'll do while Basu says, which was mentioned, which is that this is a very, very special year for us, because with this event and the events later in the week, we launched the Platinum Jubilee celebrations of our institute's founding in 75 years ago. And also, to mark those events, we are flagging off a new website, and I think Professor Basudev has been leading the effort there. So Basu, thank you, and tell me what I have to do in that role. So just go Control Tab. So that's on the website. So I have to press something. Right. Okay. So read from here. I hope this works. So this is the new website. It's a website for all of TIFR. And I want to say especially all of TIFR means not just Colaba, it means Colaba and all the centers. And really this is the website, okay, for it. You'll see all the centers as well. You'll see Colaba as well. And so, this is the portal we hope people will come to as a gateway to all of TIFR. And all right, you can see there are interesting various sections to it, including highlights of research and what's going on, what we hope to do, what's happening this week, what's going to happen in the future, and so on. And well, perhaps Basu, you should say a little bit.
All right.
Yeah.
So that's welcome everyone. So that's our new website. This is the website for the entire TIFR system, so to say. You can see that first of all, this is somewhat more minimal. We will have more updated news items coming up in the banner here. And these are links to the main campus and then to all the other centers. Spotlighted news items, these will update as we go on. And then you could go and look at more news or more science items. And just to show you what would happen to the Colaba webpage, so you go here and that takes you to the new Colaba webpage. This is the webpage for Colaba now. And here you have events, the public events and the conferences and seminars and colloquia, notice board specifically for Colaba, and then the news at Colaba, and then, for example, if you want to look at career options at Colaba and so on and so forth. So 2 new websites, that's all we had to say. Thank you very much.
When does the website actually get operational? Okay, it'll get operational in 3 days. If you look today, you may not find it, but give us 3 days or so. Thank you.
Thank you, Professor Trivedi. We now come to the first part of this afternoon's program, a new feature that was introduced in 2014 to appreciate the academic achievements of our students. We would first like to recognize all the students who have graduated from the TIFR in the past year, followed by the academic awards ceremony. Kindly join me in welcoming Professor Amol Dighe, Dean Graduate Studies, on stage. Professor Dighe will highlight all the degrees awarded this year.
So it's a pleasure for me to announce the achievements of all our students who have received their degrees in the last 1 year. As you know, although we have been in university for about 17 years now, we do not have a formal convocation ceremony. The reasons are manifold, one of them being that since most of our students are PhD students, they leave at random times of the year and it's very difficult to coordinate them coming here at one time. However, this is perhaps the most appropriate time of the year, the Founders' Day, when we can actually celebrate their achievements and the fact that they have got a degree in the last year. So I will go through the names of the students and we will appreciate them with a round of applause at the end. So last year we have given about 49 PhD degrees. 14 students have got PhD plus MSc because they were in the integrated MSc PhD program. 46 students have got MSc degrees and 2 have got MPhil degrees. So you will notice if you add them up that now we have been regularly crossing the number of 100. This is in fact more than 115. Okay, so our numbers have been growing from 1 degree which was given in 2004 to about 115 that I have given now. PhD degrees in physics have been obtained by Jishnu Bhattacharya, Shreya Banerjee, Shayantani Bera, Vikas Chand, Vishwesh Tarsare, Shamik Bhattacharya, Shiroy Shamak Tata, Deep Sarkar. We also have Ashish Shukla, Sharad Shankar, Disha Bhatia, Rohit Sharma, Archak Purkayastha, Abhirup Ghosh, Aritra Kundu, Sudeep Ghosh, and S. Ganga Prasad. Physics, we have a MSc PhD integrated program, and these degrees have been obtained by Tanay Roy, Moinuzzaman Sheikh, Chandrodaya Chattopadhyay, Ronak Soni, Ritam Sinha, Manibrata Sen, Shubhajit Majumdar, Yogesh Dandekar, and Launit Janagal. In physics, this year we gave one MPhil degree which was obtained by Siddhesh Ambire. MSc degrees in physics have been conferred upon Tuni Chakraborty, Mohit Gupta, and Pratik Mukherjee. In biology, the PhD degrees have been given to Clyde Pinto, Suranjana Pal, Parul Sood, Rohit Surtekar, Snehal Karpe, Prashant Jethwa, Amit Singh, Minakshi Iyer. We also have Kritika Falnikar, Ajoy Aloysius, Prachi Thatte, Mridula Sane, Yadugiri, Vishak Datta, Calvin Rodrigues, and Alok Javali. The integrated MSc PhD program in biology, the 2 degrees have been given to Shaunak Devta, Divya Pathak, Giselle Fernandez, Preeti Ravi, and Steffi Manjila. MPhil degrees in biology has been given to G. Ashwini. MSc degrees in biology have been given to Ayan Barbora, Vikram, Rohit Shashidharan, Disha Hiregange, Harshita Kaul, Aditya Chhatre, Jaspreet Jaswal, and Shubham Seal. More MSc degrees in biology have been obtained by Shripta Mukherjee, Janak Raj Bhattarai, Sonali Salvi, Shukrita Deb, Manisha Goel, Shiksha Azmera, and Furqan Khizar. In biology, as we know, we also have a wildlife biology and conservation program which runs at NCBS. Here, the MSc degrees have been obtained by Abhirup Khara, Abhishek Gopal, Chaksoldam Odanklan, Chayant Gonsalves, Mayuk De, Rasika Priya, Aishna Sharma, and Akshay Surendra. Most students who have received this degree are Gopal Khanal, Ishika Ramkrishna, Ryan Rodrigues, Tarun Menon, Aditya Banerjee, Tara Rajendran. In chemistry, PhD degrees have been obtained by Anju Yadav, Rustam Singh, Ananya Rakshit, Devabrat Dhara, Devdeep Mandal, Mahak Dhiman, Ankita Das, Barun Kumar Maiti, and Viola Di Melo. MSc degrees in chemistry have been obtained by Anusha Gopalan, Sauvik Ghoshal, Nita Ghosh, Soumyajit Mitra, and Kaustav Khatua. In mathematics, PhD degrees have been obtained by Anupam Mondal, Sampat Kumar Sharma, Chandranandan Gangopadhyay, and Vivek Kumar Rai. MSc degrees in mathematics have been obtained by Pratyush Nath, Aratrika Pandey, Sandeep Soni, Siddharth Sabharwal, Sinchita Lahiri, Shubhajit Bhattacharya, Anupama Bharadwaj, Amvisa Ray, Sutonoy Chakrabarti. In computers and system sciences, one PhD degree has been obtained by Nikhil Mande. In science education, PhD degrees have been obtained by Amit Dhakulkar and Gitanjali Dhate. So these were all the students who obtained degrees in 2018-19. I think we should applaud all of them with a round of applause.
We now continue with the academic awards ceremony. TIFR Endowment Fund and TIFR Alumni Association have been encouraging the TIFR community, especially the students, by instituting awards to recognize excellence in academic performance. To give away these awards, I request the director to please come back on stage. The recipients of these awards who are present here are requested to kindly come to my right-hand side of the stage and to come up as soon as their names are announced.
So it's again my pleasure to announce the names of students who have obtained Best Thesis Awards for the last year. I know many of them may not be able to be present. However, if there are people who are going to collect the awards on their behalf, they are welcome to come and celebrate the achievements of their friends, relatives, or students. The TAA Gita Udgawkar Best Thesis Award in physics this year is jointly given first to Dr. Tanay Roy for his pioneering work in the setting up of a novel 3-qubit quantum computer using improved superconducting circuits. Tanay is not here, but we have R. Vijay Raghavan, who is his PhD advisor. So, Vijay. The award is also jointly given to Dr. Manibrata Sen, who I am proud to say happens to be my own student, for his work on nonlinear neutrino flavor oscillations inside a supernova and his analytic solution by mapping to a simple mechanics problem. Honorable mention for physics is also presented to Dr. Moinuzzaman Sheikh for his studies of dynamics of ultra-short superluminal electron pulses through a solid and pioneering a tabletop method of studying ultra-relativistic electrons. Yes. Okay. Is Kamlesh Jana in the audience? Moinuzzaman had said that maybe Kamlesh will like to accept the award on his behalf. Huh? Oh, here he is. Yeah. Moinuzzaman. Another honorable mention for the physics award is given to Dr. Archak Purkayastha for his studies of a quantum system coupled to thermal baths at different temperatures, comparing different techniques to calculate transport coefficients. Archak is a student of Professor Abhishek Dhar from ICTS and is one of the first PhDs that we got from our new center ICTS since it was sold. In biology, the TA Zita Lobo Memorial Award is presented to Dr. Shaunak Devta for demonstrating that the SIRT protein has different isoforms and isoform specific functions, and for showing that the CDK1 kinase gets acetylated by SIRT to prevent cell cycle progression. Shaunak Devta or his advisors, if present, is Ullas here? Okay. The award is also jointly presented to Dr. Preeti Ravi for identifying and characterizing a uropeptide that's important in regulating insect flight, and for addressing how store-operated calcium NT is controlled in dopaminergic neurons to regulate flight time. This is a student from NCBS. In chemical sciences, the Best Series Award is presented to Dr. Palas Roy for his dissertation elucidating the molecular scale reaction coordinates controlling photo-induced charge generation processes in organic pi-conjugated polymers using ultra-fast femtosecond spectroscopy. Palas Roy is a student of Jyotishman, and it looks like his colleague is coming up to take the award. Let's clap for Palas. The award is also shared by Devabrata Dhara for his dissertation introducing novel synthetic methodologies of multiple bonded non-metal heavy main group elements and their activation by N-heterocyclic carbenes. I must also mention that he is one of the first PhD students from our Hyderabad, TIFR Hyderabad or TCIS. In mathematics, the TAA Harishchandra Memorial Award is presented to Dr. Arka Malik for his contributions to the study of nonlinear elliptic equations with singular potential, specifically to Hardy and Leray-Tudinger inequalities. Arka is a student from CAM, Bangalore. Honorable mention for the TAA Harishchandra Memorial Award in mathematics is presented to Dr. Rahul Gupta for his contributions to the study of Chow groups with modulus and K-theory for singular varieties. Is Rahul or his advisor in the audience? I do not see. In the field of computer science, the TAA Susskind Award is presented to Dr. Nikhil Mande for his fundamental contributions to our understanding of XOR functions and their circuit and communication complexity. His advisor is Professor Arkadev Chattopadhyay, and I do not see him in the audience. Okay. So that concludes the best thesis awards in all the subjects, and perhaps let's have a round of applause for all the awardees.
I request you to be please on stage. Thank you. Apart from the best thesis, the TIFR Alumni Association and Endowment Fund have also instituted other academic awards. I now request Professor G. Ravindra Kumar to kindly announce these awards.
Thank you. The TIFR Alumni Association is very proud to be associated with these awards, and it's been our endeavor to recognize the best among the kind of work that's done by our students, our colleagues across fields. And before we give away these awards, I just want to restate that on November 1st and 2nd, we are bringing lots of alumni back to the campus to celebrate the 50 years of our graduate school. So it's a major event this is the first event of the 75th year, and that will be the second event and probably the major event involving the alumni. So I would like all of you to be present there, to interact with them, to see how they have progressed in their lives and what advice they have to offer as we go forward. So let me begin with the first award. These are Excellence in Teaching Awards that we have instituted a few years ago. And it's a matter of pride for us that teaching is done out of passion at TIFR. It's not a regular activity. And to see that we have outstanding teachers is really a great pleasure. So the first award is to Professor Nitin Nitsure, who needs no introduction to this audience. And Professor Nitsure for profoundly enriching the school and its students by enthusiastically and masterfully sharing many a deep insight through a diverse array of excellent courses over several years in the School of Mathematics. Congrats. So the next award, the B.M. Udgaonkar, TIA B.M. Udgaonkar Excellence in Teaching Award in Biology for this year, goes to Professor Vidita Vaidya, Department of Biological Sciences, for her outstanding contribution towards teaching basic and advanced neuroscience courses. Her teaching opens a window of excitement for neophytes through stimulating lectures on seminal discoveries in neuroscience and the open questions in the field. Congratulations. The next award is for physics. The TIA B.M. Udgaonkar Excellence in Teaching Award in Physics 2019 is for Professor Shiraz Minwala. Is he around? Okay, any of Shiraz's countless students in this audience, colleagues? Shall I invite Amol to actually take this? So I invite the Dean Graduate Studies to receive this award on behalf of Shiraz for teaching many and varied courses on advanced topics like quantum field theory, general relativity and string theory. His deep understanding of science and immense enthusiasm communicate themselves to the students through his lectures and have set many of them on the path to their future careers. Congratulations. So these are the, yeah. So the next category is the Kaushik medals. These were instituted by Professor Ramnath Kaushik several years ago, and they've been running successfully for about 6 years now. And this is for the best paper in different subjects. Earlier it used to be that all subjects were clubbed together and we used to choose 2 medals. One is the Ramakrishna Kaushik medal and the Saraswati Kaushik medal. But of late we have decided to segregate the subjects and rotate them through the years. So this year the subjects were physics, biology and chemistry. So we have chosen one medal to be given this year, which is the Saraswati Kaushik medal, and which is being awarded to Dr. Indranuj De for his paper, Highly Efficient Broadband Terahertz Generation from Ultrashort Laser Filamentation in Liquids. So Dr. De is not here, but may I invite his co-author, Kamlesh Jana, to once again come up here and receive the award on behalf of Indranuj Dey. Congratulations. And we have more? Okay. Okay, now we have awards for younger students in the first 2 years. And the Professor Sukumar Biswas Award for Excellence in Physics. So based on the first year performance in physics in the graduate school, 2019, is presented to Aparajit Chandrasekharan for securing the highest score in graduate courses in the PhD program in physics. And among the integrated PhD students, we have Professor Sukumar Biswas Award for Excellence going to Mrs. Rijita Das for securing the highest score in the graduate courses in the integrated MSc PhD program. Congratulations. And this award is for the best seminar in the astronomy, in the areas of astronomy and astrophysics. And this is called the Ratanbhai Jerajani Award for this year, 2019. And that goes to Mr. S. Abhimanyu. Congratulations. Thank you very much. And once again, looking forward to seeing all of you back in this auditorium on November 1st, right? 9:30 a.m. in the morning. It lasts, it's the whole of November 1st and then half of the Saturday till about lunchtime. So please come and make this event very successful. Thank you.
Thank you all. Before we go ahead with the remaining awards, we will break for a lecture by Professor Jayaram Chengalur from NCRA on evolution of gas content of galaxies. The talk is on evolution of gas content of galaxies, a problem for big telescopes. May I request Professor R. Vijay Raghavan to introduce the speaker.
It's a great pleasure to introduce Professor Jayaram Chengalur from the National Center of Radio Astrophysics in Pune. Professor Chengalur obtained his B.Tech degree in electrical engineering from IIT Kanpur in 1987, after which he moved to Cornell University for his doctoral studies, where he completed his PhD in 1994. After that, he was a postdoctoral fellow at Netherlands Institute of Radio Astronomy in the Netherlands before joining the National Center for Radio Astrophysics in 1996. His main research focus is in extragalactic astronomy, particularly studies of nearby dwarf irregular galaxies, neutral hydrogen absorption in very high redshift galaxies, and in general studies of the evolution of the neutral hydrogen content of the universe. He also works in the areas of cosmology, the interstellar medium, and fundamental constant evolution. Today, he's going to be telling us about a new problem for big telescopes, which is basically the evolution of the gas content of galaxies. I would like to invite Professor Chengalur to come on stage and deliver his lecture.
Thank you, Dr. Vijay Raghavan. And I'd also like to thank the organizers for inviting me to give this talk. It's a great privilege to be here today and talking about the work that we've been doing at NCRA. I'm going to talk about, as advertised, the evolution of the hydrogen content of galaxies, and I'm not going to try and give a broad review of this, but rather I'm going to focus on the work that we have been doing at NCRA. And it's work that we've been doing for a couple of decades now, and so there are a very large number of collaborators who I need to acknowledge. I haven't put a complete list on this slide because it would take many slides to put all the names. But I particularly wanted to highlight these names. Professor Frank Briggs from Australia, who has been collaborating with us for quite some time. His students, Philip La and Zhonghua Ri. And also for the recent work, which is what's the main focus of the talk today, Apurba Bera and Aditya Chowdhury, who are PhD students, and my colleague Nasim Kanekar, who's been also one of the main driving forces behind this work. All right, so let me just start with a sort of very basic sort of big picture about galaxies. So if we talk about galaxies and we say, I'm looking at galaxies, people imagine that you're studying stars because most people think of galaxies as a collection of stars. So for example, which is probably well known, our own Milky Way galaxy has 100 billion stars. But our Milky Way galaxy and most galaxies have many, many other things in them also. And if you look at the baryonic content, the most important other component is the gas, which could be either atomic hydrogen or molecular hydrogen. And in the parlance, atomic hydrogen is called H1, and I tend to slip into that jargon quite often, so I just wanted to highlight it. So when I say H1, I mean atomic hydrogen. There's also ionized gas, cosmic rays, magnetic fields, dark matter, all kinds of things which actually go up to make a galaxy. And all of these constituents play a very important role, an active role in the evolution of a galaxy. So if you want to understand the evolution of the galaxy, you actually need to trace it in using many, many tracers. And to just give you a flavor for this multi-component nature of galaxies, I'm showing you over here an image which just shows you the atomic hydrogen and the stars in a pair of interacting galaxies. So the stars are shown in this photograph over here, which is in black and white, and it's like a negative, so it means that the darker bits are brighter. So this is where most of the stars are in these two galaxies, and the red is a GMRT image of the atomic hydrogen in galaxies. And you can see that it's significantly more extended than the stars, and the gas from this galaxy is getting pulled out and getting drawn into the other galaxy. From here you have a large counter tail, and the hydrogen obviously is playing a very important role in the interaction and merger of this system. So we made that image using we are tracing hydrogen in that image. So so I just wanted to say very briefly how is it that we're able to observe hydrogen in distant galaxies. So hydrogen, as you know, has a proton and an electron, both of which have spins and associated magnetic moments. So they could have two configurations for this, that the proton and the electron spin could be aligned or they could be anti-aligned. These two systems have, these two configurations have slightly different energy, and so when the atom goes from one to the other, it emits a photon with a characteristic wavelength of 21 centimeters or a frequency of 1420 megahertz, which is a radio frequency, and so therefore you could use this transition to sort of observe hydrogen in distant galaxies. The universe, as we all know, is expanding. So if I have a distant galaxy, it appears to be receding away from us, and therefore the light that it emits gets shifted in wavelength. And so these radio waves similarly would get shifted in wavelength to longer wavelengths or to lower frequencies. So if I were observing a distant galaxy, I would observe it at a frequency lower than 1420 megahertz. So this line is a very, very important spectral line in radio astronomy. And if you look at the observing programs of most telescopes which operate at this frequency of 1420 megahertz, you'll find in all cases that one of the major programs running on this telescope is to use this 1420 megahertz line for observations of H1 in nearby galaxies. But that's not what I'd like to talk to you about today. I want to talk about using this line to observe distant galaxies, right? So, if I want to observe the atomic hydrogen in distant galaxies, it turns out it's a very difficult thing to do because the line is actually intrinsically extremely weak. And even using the largest telescopes that we have, like the Giant Meter Wave Radio Telescope, you can only detect it in quite nearby systems. And in fact, if you look at the state of the art today, there are detections of this line in only a very small handful of galaxies at redshifts greater than about 0.2. And these have been obtained using very, very long, hundreds of hours integrations with the existing radio telescopes. It's not really practical or feasible to use these telescopes to try and observe a large sample of distant galaxies. What you really need is a much larger radio telescope, and I'll come back to that time and time again in my talk. But I did want to mention before I went ahead that there's another way of measuring the hydrogen in galaxies, and that is to use not the radio line but the UV line. The atomic hydrogen will also absorb in the UV. That cross-section is actually extremely large compared to its absorption in the radio. And so even if you have very small amounts of atomic hydrogen in intergalactic space, and you have a distant UV source, it actually produces quite easily detectable absorption by the Lyman alpha. And you actually have quite a lot of UV sources in the universe. Nature has provided them for us. They're called quasars or quasi-stellar objects. And so if you happen to have a galaxy which lies between you and a distant quasi-stellar object, a distant QSO, you can observe the absorption in Lyman alpha from the rising in the gas in this galaxy, and therefore you could sort of get an idea of how much gas is there in the universe, in that little bit of the universe, by counting how many absorption lines you get from that little bit of the universe. The thing about using the Lyman alpha line to measure atomic hydrogen, however, is that you can only use it for distant objects. You can only use it for objects which are further than about a redshift of 2, because at that redshift, the UV redshifts into the optical. And once it's in the optical, you can observe it from the ground using ground-based telescopes, and you can get good statistics. Below a redshift of 2, the line is still in the UV. The atmosphere is opaque to the UV, and so you can only observe it using satellites, which have relatively small telescopes, and so it doesn't give you very good statistics. So if you actually ask the question, what do we know about the atomic gas content of the universe, it turns out we have some idea what it's like below a redshift of somewhere around 0.2, 0.1 to 0.2, and we have a reasonable idea of what it is like above 2. But we don't really know a whole lot about what's happening in between. So that's what I'm showing you in this graph over here. So this is the atomic density, the density of atomic gas and atomic hydrogen in the universe as a function of redshift. You can see we have a bunch of measurements at low redshift. All of these come from the radio measurements of the 21 centimeter line. You have, again, a number of measurements at redshifts above 2, which again have good, reasonably good statistics. But if you look at this region in between, there are very few measurements, and you can also see that they are not very accurate. The error bars are quite large. Redshift basically measures time. It's measuring the age of the universe. And so another way of looking at this is to sort of plot time on the same axis. So, it's either time in the units of redshift at the bottom or time in units of gigayears on the top. And in a way, it's sort of, more illustrative to look at time in gigayears, because then you can see that this region where you actually have very few measurements stretches from about a gigayear to about 10 gigayears. The universe itself is only about 12 and a half gigayears old, right? So for a large fraction of the age of the universe, there's actually no good measurement of the atomic gas content. And that's really the question that we are trying to address. All right, I said right at the start that, if I wanted to understand galaxy evolution, you have to look at what's happening to all of these components. And I just wanted to illustrate the way that works. So for example, over here, what I've shown you is an astrosat image in UV of a particular galaxy, NGC 2336. And if you look at it, you can see what you see really very clearly are these very pronounced spiral arms. And the reason for that is that UV radiation is produced largely by young hot stars. So when you take a photograph of a galaxy in the UV, what you are seeing is the location of its star-forming regions. Where are the stars forming now, right? And they're forming in these spiral arms. So what is happening is basically that the gas in this galaxy is collapsing to form stars. It's collapsing where the gas is the densest. It's the densest in the spiral arms, and that's where it forms stars. So as time goes on, what's going to happen in this galaxy, as that galaxy evolves, the gas will gradually get depleted into stars, right? And eventually you will be left with a situation where there's insufficient gas left to produce any more stars. So star formation would cease, and in a sense the galaxy would sort of become passive, right? Unless there is some way of feeding gas into this galaxy from the intergalactic medium. So when you're studying galaxy evolution, these are the kind of things you'd like to answer. That is there, feeding of gas going on from the intergalactic medium? Is that happening steadily? Or is it that the galaxy had a certain amount of gas to start with, and then it just gradually fades away? Right? So if we had radio telescopes which were capable of observing the atomic gas content of galaxies, we could directly answer that question, but we don't. What we do have, however, and these are things which have been quite well measured, is how does the star formation in the universe evolve with time, right? So this is telling us how fast gas is getting consumed in galaxies. And again, so this is the star formation rate on the vertical axis. This is time on the horizontal axis, in redshift at the bottom and in giga-years on the top. And you can see what's happening is that there's a very pronounced peak of the star formation rate. Somewhere around a redshift between 1 and 2, there's this huge burst of star formation in galaxies, right? It's called the epoch of galaxy assembly. That's the point at which about half of the galaxy gets its stellar mass, right? Most of the stars in the galaxy are formed at that point. And after that, you can see that the star formation declines quite sharply. And by the time you reach the current epoch, the star formation rate is almost a factor of 10 lower than what it was at its peak. Right, so one of the questions you'd like to answer is this happening because of a decline in the gas content? Because the gas is basically getting depleted. And as I said, it's very difficult to measure because this entire region is exactly where it's very difficult to measure the atomic gas content, because neither the 21 centimeter line nor the Lyman alpha line works for you. The 21 centimeter line doesn't work because your telescopes are not sensitive enough. The Lyman alpha line doesn't work because it's still in the UV in this range, and you can't observe it with ground-based telescopes. So what you really would like is to have very, very large radio telescopes. And again, on this occasion, I thought it would be very nice to highlight the fact that one of the first people to recognize this was Govind Swarup in 1994. So he writes over here that what you would really need to solve this problem, he's given a couple of solutions. I want to pick this one, where you build an array, he says, of 400 antennas, 50 meters diameter. That's basically something 10 times bigger than the GMRT, right? And this is in the midst of building the GMRT itself that Govind has, sort of looking ahead, and he's saying that, okay, the GMRT will do certain kinds of problems, but to really tackle this problem, which is one of the outstanding problems in radio astronomy, you're going to need something 10 times bigger. Right? And this is, a theme which many people across the world began to take up. Govind was one of the first, if not one of the, if not the first people to point this out. But, gradually people began to sort of converge around the fact that you need a much, much larger radio telescope to solve a number of outstanding problems in radio astronomy, including the one that I'm talking about today. And they've come together to form this consortium to build the next generation radio astronomy instrument called the Square Kilometer Array, of which NCRA TIFR is the lead partner. Right, so this is one option we could take, that this is an important problem, this is an interesting problem, we should do it. And to do it is going to take a really big telescope. So let's put all of our strength together and let's build this big telescope. And as I said, this is indeed a path which we are following. But in parallel, you'd also like to ask the question that is there really nothing we can do with the telescopes that we have today? And that's really what I'm going to talk about for most of the rest of my talk. What is it that you could do to try and address this problem with the facilities, with the instruments that you have today? And as I said, this is the thing that has been going on for the last couple of decades or so at the JMRT. So the basic idea is the following, that if I pointed a telescope in some random region of the sky and I observed it, it's not that there's only one galaxy in that region. There are many, many galaxies in that region. Right? That volume of space that I observe when I point my radio telescope at any random region of the sky actually contains a large number of galaxies. Right? And so even though no individual galaxy could be detected, the average H1 emission from these galaxies actually is measurable. And so, for example, if I actually knew the 3D positions of all of these galaxies, if I knew where in space they were and what exactly their redshift was, I could sort of stack all of their spectra together. I could align them, add them all up together, and I should be able to detect that average signal. And so, as I said, that requires the 3D position to be known, 2 sky coordinates, and a redshift. So the idea, again, if I just were to give a cartoon, that say I have 3 galaxies in my field of view, and they are at different redshifts. So that means one of their H1 lines comes here, the other one comes over here, and the third one comes over here. If I know exactly where I expect those lines to be, I could align all of them up. And so I've aligned the lines, I've added them up. So then the line adds up, the noise sort of averages down, and you're able to see the average emission from those galaxies, even though none of them have been individually detected. Right, so this, we tried a proof of concept, as I was saying, almost 2 decades ago, where we looked at a cluster of galaxies. And at that time, the only region of sky where there was a large density of galaxies whose redshifts were accurately known were clusters of galaxies, because people were studying clusters of galaxies for other reasons. They wanted to understand how these clusters formed, how they evolved, and so on. And so because of that, you could have a region of sky where you had hundreds of redshifts, and your radio telescope could observe it at one go. So that's what we did. We looked at this particular cluster, and we did indeed detect the average signal from all of those galaxies, although no individual galaxy was detected. And it's not just that we detected the average signal. We could say all kinds of things about how that cluster was formed. So for example, we found that the signal was maximum when we looked at star-forming galaxies that lay outside the core of the cluster. And this is exactly what you would expect in models where galaxies are falling into the cluster for the first time, because clusters of galaxies contain not just galaxies, they also contain hot X-ray emitting gas. So when a galaxy from outside the cluster falls into the cluster, and it moves quite fast at speeds of several hundred kilometers per second through the cluster, the atomic medium in the galaxy gets completely stripped out by the intercluster medium by ramp pressure stripping. So you would expect that the galaxies where you do have a lot of gas are the ones which are just falling into the cluster. They haven't yet gone in through the cluster, and that is indeed exactly what we see. And in fact, if we asked ourselves the question, which are the most gas-rich galaxies in the cluster, they actually turn out to be in a group lying somewhere in this region, and you get a really pretty bright signal from the galaxies over there. And that, again, is sort of in keeping with our understanding of hierarchical formation of these galaxy clusters. What is happening over here is that a gas-rich group of galaxies is, as a whole, sort of falling into the cluster. It will eventually merge into the cluster and make the cluster still bigger than what it is today. Right? So sort of emboldened by this, we then went on to try and move further out distances with the JMRT. And so the first thing we tried was to measure the H1 content of field galaxies at a redshift of about 0.2. We had 121 galaxies in the volume that we were able to probe. And that volume is actually limited by the redshift range that your instrument is able to look at. And the JMRT, as it was built, gave you 32 megahertz of bandwidth. So you had 32 megahertz of bandwidth, around 400 megahertz, and that's actually quite a small redshift range. So we have this tiny slice in redshift which we are looking at, and we have 121 galaxies over there. We had to get the redshifts for our galaxies ourselves, because you need quite accurate redshifts in order to align everything together and add it up. And so, so then there was collaborators who we worked with to get the accurate redshifts and so on. And so all of this makes this a project with quite a large lead time, and a fair bit of effort by a lot of people to sort of make it all happen. Although we had 121 galaxies, because the volume was small, actually most of these galaxies were faint, right? If you have a large volume, then you will have a number of bright galaxies in it. If you have a small volume, you have quite a few galaxies in it, but many of them are actually quite small, they're quite faint, which means they have low hydrogen mass. And so all in all, it sort of makes it, even though you have 121, it's not all that easy to detect even sort of the average H1 content. And all we ended up with was a tentative detection of the stacked H1 signal. And somewhat weak constraints at a redshift of 0.2, but they were still interesting because at that time there were no other available constraints, right? So these were one of the first constraints we began to get at those redshifts. This is just the tentative detection that we have of the co-added signal. We did a number of others. I'd just like to point out one more, which is at a redshift of 0.3. And again, very similar, radio observations done with the JMRT, redshifts which had to be obtained are fresh. Not a very, very large number of galaxies, about 165 galaxies. And we have over here, this is the measurement, which is just about beginning to reach 3 sigma, right? So, towards the end, we are beginning to approach sort of a statistically significant detection of the atomic gas content, and now at a redshift of about 0.3. In parallel, of course, the optical astronomers are doing their thing, and they are also surveying the universe for their own reasons to study, for their own studies of galaxy evolution and so on. So by this time, there were a number of deep redshift surveys available, and Nissim and his collaborators was trying similar techniques at slightly higher redshifts, at a redshift of about 1. So these were fields selected from the Deep 2 galaxy redshift survey. So over here, the galaxy redshifts are already available to you. Because it's at a larger redshift, you actually get a larger volume for the same bandwidth. And so they have a total of about 857 galaxies which they stacked, but nonetheless you don't quite end up with a detection, but you get to upper limits which are interesting. So this more or less summarizes where we had reached with the JMRT, right? And what I'm going to talk to you about now is what we have been doing over the last year and a half with the upgraded JMRT, right? So I'd like to say a little bit about the upgrade to the JMRT. But to place that in context, I have to tell you a little bit more technical details about the JMRT itself. As I mentioned, its bandwidth that we were using was about 32 megahertz, which corresponds to a relatively small slice in redshift space. And so a single observation only occupied, gave you a small volume of space, only a few hundreds of, only of the order of about 100 galaxies, many of which were small and hence intrinsically faint in H1 emission. What would really make a difference to our project was if we were able to observe a larger instantaneous volume. Right? And that exactly is what the upgrade provided. So if you looked at the old JMRT, it's the same is true for the new JMRT, that basically you have a parabolic mirror over here. The radio waves come and hit the mirror and come to a focus over here. At the focus, we have another antenna, which sort of converts the radio waves into an electrical signal. And these small antennas, which we call feed antennas, were quite narrow band in the old GMRT. So you could observe only a small range of frequencies. And of those range of frequencies, you could observe at any one given time only about 32 megahertz. So over the last decade, the GMRT has been very significantly upgraded. And what we have now is basically, almost a new telescope. Pretty much everything has been changed from the servo system, where we have new brushless DC motor burst servo systems, new broadband feed antennas. So these are feed antennas designed and built at the GMRT, which are much more broadband than what were there earlier. New amplifiers, which are low noise and also broadband, a large, bandwidth optical fiber transport system, 400 megahertz, 400 megahertz of analog signal conditioning to get the signal to the right level and so on for you to digitize, and finally a hybrid digital backend, FPGA GPU-based digital backend, which absorbs and can process 400 megahertz of data at one time. There's also the last piece which has just been put in is a new control and monitor system, which has been built as a sort of a prototype for the SKA control and monitor system. So often we like to say that actually it's, everything excepting the concrete and steel of this telescope has been changed. But even that actually is not a completely true statement, because for a number of antennas, we've even changed the steel, we've changed the reflecting surfaces, and that has again given us a small but significant improvement in sensitivity. So in many ways, really, we are dealing with a completely different telescope than what we were 2 years ago. And to give you a feel for that, I'm just showing you the range of bandwidth, amount of bandwidth that you can observe at a given time. Maybe we could just focus on these numbers over here. This is telling you the fractional bandwidth that you can observe at any given time. So that means around 1400 megahertz, you have a 1/3 fractional bandwidth. Earlier, you had a fractional bandwidth of the order of 0.02, 0.03, as I said. So now, rather than observing just a tiny part of the band, you're able to observe a third to close to a half of the band, depending on which frequency you're looking at. All right, and just to complete the story, let me just say what happens to the telescope sensitivity when you do that. If you're looking at continuum sensitivity, because you now have a bandwidth which is more than a factor of 10 bigger than what you had earlier, the sensitivity improves by about a factor of 3. Your imaging fidelity also improves for technical reasons that I won't get into. And so what you have effectively now is basically, if you look at the sensitivity of the telescope, so it's sensitivity in some units plotted on the vertical axis as a function of frequency on the horizontal axis, and lower numbers are better, right? And it's a very busy diagram, but basically what has been plotted is the sensitivity of various telescopes all over the world. The pink dots are the ones I want you to look at, and you can see that the pink dots are typically the lowest at their frequencies, right? So this makes the JMRT one of the most sensitive telescopes in the world at all these frequencies of operation. The only thing which is more sensitive than the JMRT are these 3 triangles, and these 3 triangles are the proposed square kilometer array, which I had been talking about. This is some theoretical point which we need not look into. Right? So basically, of all the existing telescopes, we are now dealing with one of the most sensitive ones. But this is for continuum observations. If you're looking at a spectral line, the fact that you've increased the bandwidth doesn't improve your sensitivity, because your spectral line is narrow. All that matters is how much sensitivity do you have in that frequency band. The fact that you have the same sensitivity over a large band doesn't help you. Right? So we are dealing, in that sense, for spectral line observers, not a whole lot has changed. It's become slightly more sensitive because our feeds and receivers are slightly better than before, but it's not this dramatic factor of 3 improvement. On the other hand, if you're doing these kind of stacking analyses where you're averaging all of the galaxies in the volume, then you have a big gain, right? Because you're now increasing by almost an order of magnitude the redshift range that you're going to probe in a single observation, right? So it really now is going to make a big difference. And now let me just show you what we get, when we observe with this new telescope. So what I'm going to show you is from the PhD thesis of Apurva Bera, who would be finishing this year. He's really done an astonishing job with the data that we have. We looked at a field with galaxies with redshifts less than about 0.4. We have 445 galaxies in this field. They are all relatively bright, blue star-forming galaxies. The median redshift of the sample is about 0.34, and when you stack all of them together, you get a really nice detection at about 7 sigma. It's the first statistically significant detection of the average H1 content of star-forming galaxies above a redshift of 0.2. And after all these years of upper limits and 2 sigma and 3 sigma kind of things, it's really nice to start dealing with actual detections and moving on to do various kinds of science with them. So here we have a good measurement of the average H1 content. That's not all, because we've observed a 400 megahertz bandwidth. In addition to the line, we can also measure the radio continuum, and Apurva has done a really fantastic job over here. This is his radio continuum map. Every little dot over here is a source. The RMS noise in this map is about 2.5 microjanskis, and this not only makes it the most sensitive image made with the GMRT, it's also one of the deepest images at this frequency made with any radio telescope anywhere. And so, the measurement of this, the radio continuum from the galaxies allows you to measure its star formation rate. So then you can measure how much time does it take for the gas to deplete. And the gas depletion, it turns out, has not evolved very much between 0.3 and the local universe. The gas depletion time is about the same. All right. Now let me move on. And now we move not to redshifts of 0.4, but to a redshift of 1. And this is the PhD thesis of Aditya Chowdhury, who's sort of halfway through his thesis. And so we went back and observed the same fields that we had looked at before, the deep 2 galaxy fields. The difference now is that instead of observing the small slice of redshift space, we are able to look at a very large slice of redshift space. The total integration time we have is extremely modest, only about 60 hours on source, but we have about almost 8,000 blue star-forming galaxies that we've stacked together, or an order of magnitude more than that you had with the old GMRT observations. And again, you have a very nice, beautiful detection of the average H1 content of these galaxies. And so that, again, is really nice. I mean, this is in the middle of this range where everybody has been wanting to measure the stuff, the atomic gas content of galaxies, and we have the first measurement right here. All right, so again, the same as for the 0.4 measurements, the star formation rate in these galaxies was measured from the radio continuum, which came, in a sense, for free with the same observations. And we were able to measure the gas depletion time. And now we see a big change. The gas depletion time is only about 1 billion or 2 billion years. That means that these galaxies over there at about a redshift of 1 cannot sustain that star formation rate for a long period of time. And so that means that the observed rapid decline in the star formation rate is sort of consistent with the idea that the gas reservoir is getting depleted. In about a couple of billion years, they'll burn through all of the gas that they have, and the star formation has to then start falling. Right? These measurements also allow us to do a robust determination of the gas content of the universe at a redshift of 1. This is a similar plot to what I'd shown you at the beginning, that the average atomic gas content on the vertical axis, time on the horizontal axis, either as redshift at the bottom or look-back time on the top. This was the region where we didn't have a whole lot of measurements. All of these points are from the GMRT. This is Nissim's upper limit. This is the raw measurement that Aditya has, which just tells you how much gas there is in the galaxies that we have sort of averaged together. But we also need to correct for various incompletenesses in the sample. And so when you do that, this is the measurement that we get. So this is basically what we believe is the average gas content of the universe at a redshift of about 1. And you can see there's a very dramatic improvement in the accuracy with which we are able to sort of make that measurement. All right, and so looking forward, so as I said, the results that we have just presented are from a relatively modest investment of GMRT observing time. Deeper integrations are indeed underway right at the moment. We expect that we will detect emission from several individual galaxies at a redshift less than 0.4. We should also be able to determine how the gas content depends on other galaxy properties, such as the stellar mass, the star formation rate, and so on and so forth, both at redshifts less than 0.4 as well as redshift 0.1. And so we hope over the next year to 2 years to provide a good understanding of the statistical properties of H1 in distant galaxies, well before the SK is up and running. And we expect that this should also pave the way for the deeper surveys planned with the SK once it's built to detect individual galaxies. All right, so that brings me to the end of my talk. I can summarize. Measuring the evolution of the H1 content of distant galaxies has been a long-standing challenge in radio astronomy. Detecting individual galaxies requires very large telescopes, and it's one of the key science drivers for the planned square-kilometer array. But robust detections of the average gas content, even at redshifts of about 1, is now feasible, and that's really thanks to the capabilities of the upgraded GMRT. Our pilot observations have already yielded very interesting results on the evolution of the gas and the gas depletion time, and deeper observations are in progress. Do stay tuned for more results. Thank you.
Thank you, Professor Changlur, for a really nice, interesting talk and telling us about the new enhancements to the GMRT and what they have been able to achieve scientifically. We have some time for a few questions from the audience. There are a couple of microphones we can bring by if you want to ask any questions to Professor Changlur. Maybe I will start with a question. So this, did Sandeep have one? Maybe I'll. So this technique of stacking seems to be very crucial to get the data till your overall sensitivity can be brought down. But were there other technological improvements which paved the way for this stacking technique to be actually possible? Because it seems like it's a signal processing technique and could have been done earlier. What was the major breakthrough which sort of led to this possibility?
No, the main thing really was that you needed enough galaxies. You needed to be able to observe a large enough volume at one go. And so that's why when we started, even though all of it should work in principle, we never had enough signal to noise ratio. We just needed to probe a larger volume.
So the 400 megahertz upgrade allowed you to do it much better.
Was the thing which really made the difference.
Okay. And do you see this as being now a standard practice in all radio telescopes to have this ability?
Yes. Stacking is now talked about as part of the program in many radio telescopes around the world, including the SK.
Right. Thank you.
Sorry, Jairam. I didn't quite understand what we have learned so far in terms of systematic trends as you look at galaxies at different redshifts. So just to ask you, and it might be an imprecise question, sorry about this, but I understand that if there's a galaxy and it's getting older, star formation is sort of ceasing, maybe H1 content is dying down.
Yes.
But let's say we look at a galaxy roughly at the same stage in its evolution, but at different redshifts, that is to say, early on and more recently. Is there more H1 early on?
Than early. Yeah, so that actually is, in a way, the big and the interesting question, because is it that I actually have a blob of gas at the beginning and then that blob of gas sort of just moves on, forming stars and eventually dies? Or is it that I have stuff falling in as well as stars forming and so on? And indeed, all of this seems to be happening. But at about a redshift of 1 seems to be the point at which further inflows are not really dominating anymore. About a redshift of 1 seems to be the point at which the decline in the gas content because of star formation is sort of overwhelming any little bit of further gas input into it.
Thank you.
Okay, any last questions?
There's one.
This one here.
Yeah, maybe I didn't get it properly. Your so-called old GMRT,
yes,
the present GMRT, GMRT or whatever. So what is the difference? Is it in terms of antennas or in just terms of stacking, what you explained just now?
No, the stacking was a technique which we applied only to this problem, to measure the H1 content, for which it was very important to have the increased bandwidth of the new telescope. The new telescope observes a very large bandwidth compared to the old telescope. And if you were to ask me what is new in the new telescope as compared to the old telescope, it's easier for me to tell you what is not new. Cement is not new. The cement of the shell is not new, and the steel of the backup structure is not new. Everything else is new.
Thank you.
Okay, so if there are no more questions, let's thank Professor Changlur again for a really exciting talk. Thank you.
Thank you, sir. In the next part of the event, we announce the service awards. We honor those who have completed 25 years of continued service in TIFR. The recipients of these medals are requested to walk up to the stage in the order seen on screen and to come up on stage when your names are announced. I request the Registrar to announce the recipients of the awards. I request the Director to kindly hand over the awards to the recipients.
There's a list here. I shall now call upon the lists one by one of the employees who have completed 25 years of service as on 29th October 2019. Sri S.V. Armorikar. Sri B.P. Badgeri. उनको यहाँ से जाने के लिए बोला। Sri S.Y. Bosle. Miss B.A. Chalke. Shri B.D. Chaskar. Shri M.M. Chavan. Shri D.S. Chibde. Professor Sugra Chunwala. Shri Gigi Dekate. Shri P.K. Dotre. Shri S.F. Haq. Miss Magnus Johnny. Shri John Jesudasan. Shri S.N. Kadam. Shri P.T. Kalambe. Miss Nilima Kamble. Shri Gopichand Kanagal. Shri R.S. Kamkar. Shri Prajit Kumar. Miss Pragati Mayakar. Shri D.S. Mungialkar. Miss V.G. Nimbale. Shri M.G. Parmane. Congratulations. Shri R.R. Patade. Shri A.N. Patil. It's not here. Shri B.S. Pose. Shri P.R. Powale. Shri B.S. Rao. Shri B.S. Rao is not here. Shri D.K. Salvi. Shri D.V. Sawant. Shri P.B. Shah. Shri J.C. Shilake. Miss Shobha Shenoy. Shri V.R. Swadanavar. Shri V.G. Sonavane. Shri K.V. Tulsiram. And Professor Lokesh Triberi.
Thank you, sir. I request Director Sir to please stay on stage. We come to the next segment, that is the Sport Achievement Awards. These awards are given to honor those staff members who have served the institute beyond the call of duty. I request Professor Vategaonkar to announce the recipient of these awards. I request the director to kindly hand over these.
Well, I'm pleased to announce the Sport Achievement Award for this year that goes to Santosh Chavan. Mr. Chavan's outstanding achievement during the year 1819 was for the display of initiative, enthusiasm and positive attitude and proven record of performance in his work, especially in reviving an old spray painting machine for the RPC detector without any technical manuals. This was a challenging job and he did it quite successfully. Mr. Chavan.
I request Professor Vategaonkar to also announce the Lifetime Distinguished Award. This award honors those staff members who have served the institute over their career with a great sense of dedication and diligence. I request Director Sir to please hand over this award.
This year's Lifetime Distinguished Service Award goes to the most deserving person, Mr. A.M. Bhatkar. He is from the AC department and he joined the institute in 1983 as tradesman. He has delivered an exemplary service for more than 36 years in the institute and has been inspiration for everyone else. Let me just add a few words on my own. He is the backbone of the air conditioning thing that we enjoy. I think there was a crisis time when the AC plants were down for about a week, I think, and he did a major job in putting that AC machines in operation. Mr. Bhatkar.
Thank you, Professor Vategaonkar. Thank you, Professor Trivedi. Congratulations to all the awardees. Thanks to all the presenters and the sponsors of these awards. This is an announcement regarding the Arts and Archive section exhibition. They have put up an exhibition titled A Life of Art and Learning at TIFR, which can be viewed until 13 November 2019. We are now coming to the end of this program, and I would like to invite Professor R. Vijayaraghavan to deliver the concluding remarks, please.
Thank you, everyone. Let me just request all of you to give a round of applause for all the people who have received awards for both lifetime and 25 years of service and academic achievements. So with this, we come to the conclusion of the program, and I would like to thank several people who made it this function possible. Let me start by thanking the director for his support and guidance and for being here and giving away all the awards. Also like to thank Chair ACCC, Professor Vategaonkar, for his support during the organization and also for giving away some of the awards today. A special thanks to our guest from NCRA, Professor Chingalur, for delivering the scientific lecture today. And also to the Dean GS, Professor Amol Dige and Aruna Bhattacharya, for helping get Professor Chingalur to come for this event. We have to thank a lot of the people involved in the Founders Day Committee and all the arrangements done by them. Let me start by thanking Professor Amol Dige for coordinating all the aspects of the academic part and getting all the academic awards in place and announcing them today. Professor Aruna Bhattacharya, who's been instrumental in arranging for the live webcast today, and also for all his work on organizing the science activities, which is going to happen on the 3rd of November. I'd also like to thank Ms. Bindu Jose for preparing the PowerPoint presentation and the script for the Founders Day program, along with Ms. Suchita Dikshit, who compared the program today. Ms. Bhavya Rangaswamy for arranging the archive exhibition called Life of Art and Learning at TIFR. I'd like to thank Mr. D.V. Shah for taking care of all the arrangements relating to the function today and also for November 3rd. Shri Tambeji for the high tea we're going to enjoy soon, and all the arrangements for food and snacks for Founders Day on November 3rd. Shri Bharat Joshi for the overall security arrangements and issue of special passes for family members and participants. The gardening team headed by Shri Gumasteji for all the floral and other decoration of the foyer area of the auditorium, both today and later on. All the auditorium staff for arranging the technical sound and light arrangements for today and also for November 3rd, and also being available for technical rehearsals, some of which will go late into tomorrow evening. So I'm already warning them that they need to hang around late. So thank you so much for your support. The cosmic maintenance for all their help in getting the place up and ready for the functions today and for the coming few days, as we also have the graduate school functions coming up. The TIFR guest house for arranging accommodation for our invitees from out of town, and also to the HBCAC guest house for help with accommodation, and also for agreeing to hold a science book exhibition, which I believe should be inaugurated either tomorrow or on November 3rd. If I've missed anybody, I would like to apologize, but let me thank again all the Founders Day Committee members for putting in all the work to getting this program off the ground today, and we'll continue for the next several days into November 3rd. Just a quick announcement for those of you who are planning to attend the November 3rd functions. There will be special bus services, and the notices have already been put up. I think there will be 2 buses coming from the Mandala campus on November 3rd in the morning, and then they will take you back once the cultural program will end at around 6:30 to 7 p.m. on Sunday. So with that, let me invite you all to high tea, and thank you once again for being here. And thanks again. Bye.